Good afternoon, everyone. Let's continue to discuss the blockchain, the Zksync blockchain, which is one of my favorite L2 blockchain. One of the things we talk about is we like to look at the system contract, and there are quite a few important system contract. Last time we focused on contract deployer, how we can deploy a contract, regular contract and system contract. Today we are going to look at another one called L1Messenger. We mentioned this contract a few times, which is used to send message to L2, including logging, including bytecode publishing. So let's look at how this is done over here. Why don't we look at the source code? So if we look at source code over here, we can see that one of the important function is called send to L1, which is send a message. So the input is unstructured bytes. First of all, you are going to hash it, and then also doing a before and after gas check, so we can know how much gas is spent on hashing the message using KeyCache. In addition, we are going to calculate the so-called chain message hash, which is an accumulated hash of pairwise. So it's you combine the cumulative hash with the new hash. So you end up a new accumulated hash called chain message hash. So this will be used to ensure the integrity of all the messages. Okay. And then the next one is it's going to construct a log, L2 to L1 log. This is a fixed length, which you can count how many bytes. A total of 6 fields. Shard ID a service right now is always 0 and true. The next one is you are going to contact the system context contract, another system contract we're going to talk later. This is a contract which provides all information about the current transaction. So for example, what is the transaction number in block right now for this particular transaction in execution? And then it's going to be the sender and the key value pair. The sender in this case is going to be this particular L1 messenger. And then the key is going to be the caller, whoever called this sender to L1. And then value is the hash of the message. So this is essentially creating, you can consider this like metadata for the message, the context for message. And then we are going to call process L2 to L1 log, which essentially is going to emit an event for the log. So first of all, it's going to hash the log by encode a packed bytes over here and calculates key cache hash of this. So this will also take some gas. We will look at how much gas this is going to take. This is the gas to process L2 to L1 log. Another gas is you have to combine these two hash into the cumulative one. So this is for chain log hash, it's for log. So now at least we see two accumulated hash. One is for the message, the other is for the log. And then we are going to write down how many log we are going to process. So this is the number of log we need to process. We are going to process in a batch. Every batch, we process a number of logs. So we need to remember how many logs we need to process over here, because each batch might process different number of logs. And then it's going to return log ID emoji. This is probably can be used in by offline, I believe, offline bot to create their own hash from bottom up, for example. Okay, so you will remember what is the ID of the log. Okay, and then you for every ID you're going to create a hash for the log. So coming back to this, we remember we spent this gas hash the whole log and hash the 32 byte word, because both of them is already a 32 byte word. So you combine them and do a hash. So after we have done that, when we are going to calculate because all of these need to be published on L1. So we need to calculate what is the length of the data. We call pub data, means to be published data, the length of it. And that will take out 4 bytes of the code of the length of message. Okay. So that will be over here. And then it's going to be followed by message. So this is going to be the message length. In addition, we are going to also worry about publishing the log. So this is the size of a log that we need to publish. So log, message, and the length of the message. And this one, we don't need to remember the length because it's always fixed, I believe. So that's one thing over here. All right. And then the next one is time to calculate how much gas we have to pay in order to do this. First of all, we need to hash the log. So this is a fixed length. It's called KK gas cost based on the length. Secondly, we have to combine two hash into one. To combine two hash into one, this is the gas we're going to burn, and we combine 3 times. So let's calculate with the 3 times at least. The first time is here. We combine 2 into the chain message hash. The second one is here in the log. We combine the old chain log hash with the new hash log. And then with the third time, actually the third time is going to be in the another function called a publish pub data and the clear state. This is going to be only called by the bootloader, but the gas is going to be paid by individual message. As a matter of fact, this is going to be only called for the whole batch. So that means going to for all the messages, all the bytecodes, for all the logs. So the gas that paid by the bootloader, in this case called by bootloader, needs to be compensated or paid by individual message sender. So in this case, the caller of the L1 to L2 sent to L1 need to pay their own share. So one of the share is going to be the reconstruction of the input. The reconstruction of, let me see. Okay, we're going to reconstruct the chained log hash, which is supposed to be equal to the chained log hash over here. So that's the third one. Okay, so this is why it's 1, 2, 3, but you can argue maybe 4, depending on if we need to count the gas that calculate the root hash of the whole tree of the logs. So, but that's debatable. Anyway, we come back to this 3 times, and then it's going to be also the gas to hash the whole message right in the beginning over here, this one. And then the last part is going to be based on the number of bytes we are publishing times a fixed coefficient. So this coefficient is empirical value. Is part of the configuration. And then we're going to burn the gas by calling a facility function from system contract helper, which is going to do a system call, actually. We're not going to look at this function. It's similar to other system call. And then we emit the event. So this event, including the hash as well as the message content. So this can be picked up offline of blockchain and then send it over to L2 with the integrity verification from all of these logging over here. The next one is just to send the log. So send L2 to L1 log without sending a message. So send a log is basically sending a key value pair. That's what we call log, key value pair. Both of them is a word. So the log is going to be fixed the length in 6 fields. The first field right now is fixed, is 0 and is surface. It's a little bit flexible than the message, which is always making this a service is true. But here a service is provided by the user. So this function is called only by system contract. So it's not like everyone can do a log over here. And then we create a log, L2 to L1 log. Then similarly, we're going to process L2 to L1 log, which is calculate a hash for the log, and then calculate a chain log hash, accumulated version, and then increase the number of log by 1, return the log ID, which is the old number of logs ID to process for the log. So each log is assigned with a unique log, at least within that batch. Okay, I should say it's index, because in different batch, the index will be reused. So then the question is, how much gas do we have to pay? Well, obviously, we have to pay for hashing the whole log, plus 2 combining 2 hash into 1. So the first time is calculate the accumulated hash over here in the process to log, which is right here, chain message hash, calculate accumulated version. So that's one. And the other one, the other one is, let me see. The other one is, it's going to be reconstruction. We just talked about it. You have to reconstruct the we have to reconstruct the root hash of the log. Okay, and then that will give you gas to pay, and then we burn the gas, and so on. Okay. So that's done by send L2 to L1 log. It's also done right here. It's going to be calculated as well. So let's look at next function called request bytecode L1 publication. So this one is going to publish bytecode on L1. So the first thing is similarly, you're going to calculate accumulated version of the chain L1 bytecode hash based on the old one with the new bytecode hash. And then we are going to calculate the number of bytes of the bytecode by using this utility function. And then now we are going to calculate the public length, which is basically the length of a bytecode, because it's going to be published on L1 with the encoding of the length, which is 34 bytes. And then the gas pay will be this one, which is also coming from the first component, is very likely coming from the publish, pub data, and the clear state. And then we have to combine 2, which is the first line over here, combine 2 hash. And then based on the public length, we have to pay this much, amortize the cost from this function. And then finally we burn the gas, and then we are done. Okay. So the most difficult function is this one, but when you look at this function closely, it's not that complicated. The publish pub data and the clear state is going to be called by the bootloader, which is the system contract we're going to talk about later. This bootloader right now is basically doing a processing of transactions submitted by operators or by miners. They are the one who submit all the transaction to bootloader. So bootloader will process transaction one after another in a batch fashion. So for every batch, it's going to call publish pub data and clear state with L2 dot validator, which is going to validate this data over here. So initially, we start from the call data PDI equal to 0 of the call data. And then remember, the call data is going to start with a signature. And that signature is this one. So 4 bytes encode validator pub data selector. So then we're going to skip by increase by 4. So the next one, we're going to read is the field of input chained log hash, and that must be equal to the state variable stored in this contract. And then the next one is input chained log root hash. And this one is it's going to be compared to one that we're going to create later. We're going to reconstruct the root hash for a whole tree of logs, and then we can use this to compare. The next one is input chain message hash, which is a cumulative version. We're going to compare to the chain message hash we stored already. And then similarly, we are going to do for the enchained bytecode hash, which is accumulated hash comparison. And then now it's time to read the rest of the data. The rest of the data should start from we are going to read from the next word over here. And then this offset should match the call data PTR plus 28. Why plus 28? Because call data PTR start from beginning, will offset from not counting the signature. In other words, offset 0 is not from the beginning of the call data, but 4 bytes from the beginning of the data, not counting the signature. So this is why offset should be equal to call data PTR plus 28, because call data 28 is going to be starting earlier than offset. So these two must be equal. And then once we have done that, then the offset is followed by a field called the length. So the length is going to be the length of the data we have on this call data. After that, we are going to plus CD4, because one word is for the saving the offset, the other word is saving the length. So we skip 2 words, because 64, this is where the data started. And then it started with the number of logs field. So this is retrieving the number field, which is 4 bytes. So this is why we're going to skip 4 bytes right here to really retrieve the first log. So if the number of logs is too many, because this is the maximum number of logs we can have in one batch. And then our if the length is going to be greater than this, and this length, I don't know why. I don't know why this fall over here. What is the length? The length is okay. No, here's the length, because the length also includes the first field of number of L2 to L1 logs. This takes 4 bytes. Okay, so this is why the length has to be smaller than this, because this 4 is the length, is the number of logs, the field. So so the next one is, let's talk about it's step 1, 2, 3, 4. So the first step is we are going to reconstruct the so-called reconstructed chain log hash. So before we do that, we're going to calculate the hash for every log. So this is how we hash the log over here for every log. And then in addition, we are going to move the pointer to the next one. After we move the pointer to the next one, then we're going to calculate the accumulated hash. So this is where the gas has to be amortized to the L1 to L2 to L1, and then also the L1 to L2 functions. We're going to do the match, make sure the reconstructed one is equal to the one which has been stored, And then the second step is we are going to pad the rest of the leaf hash by basically by the leaf hash for for the default. For example, for empty leaf. Okay, so that means the whole tree, the leaf level is always have this number of leaves. So then we are going to do a level by level uh, from the first level. Then every next level, the number of nodes will be reduced by half. So we are going to calculate the hash. So the hash is always going to be stored in the first part of the array, and also first part of the array, and so on. So in this way, we are able to doing like two-way merging, kind of an algorithm. Every two leaf will be merged into one parent, and all the way until only the root is going to be in element 0. We'll store the root hash of the whole tree. Okay, so that's the second step. Once we have done that, we're going to do a comparison over here to compare the input chain look hash that we read earlier from the beginning of the core data. So this reconstructed one should be equal to the one provided by the user. And then we can also calculate the aggregate root hash from L2 message root. This is not a system contract, which is going to maintain the aggregated root hash for all the messages, including the one from previous batch. So it's also another cumulative version. So in this way, you can calculate the full root hash, which is a concatenation of both of them, and calculate a new gigahash. Step 3, or maybe step 4 now, is we are going to call the L2 DA validator. So if it's not 0, if it's have input, so when you call it, you're going to provide all the gas to it, and this is the address you're going to call. You're not going to provide any MSG value, and the data is simply the whole call data of the output input. It's not a system call, so we are going to say system call is false. And it's going to return a hash. So we are going to decode the return data as a hash and save it to be called L2 validator output hash. After that, we're going to call the system to L1. Basically, it's going to create a 3-log record with the key value pair. So the key will be this one, and then the value in this case is going to be the address of the L2 validator. So that's the second log. The first log is L1. It's going to be the key, and then the value is going to be the full root hash. And then the first flag is called is surface. So this is all a surface true. And the last one, we also put in the log the output hash from the L2 validator. And then finally, we just clear all the cumulative hash, including the number of logs to process, okay? Because this is the one we iterate through to calculate the leaf hash of every log, okay? So that concludes our presentation for L1 Messenger, which is interacting with L2. Thank you so much. Have a nice day.